Good day, my angels. Last week we gave you a take-home quiz. It was a shorter week. Make sure you mark the quiz. I sent out the solution key on Wednesday, and then email me your score. And if you made a mistake on the quiz, or more than one mistake, feel free to do your corrections. Get perfect. Email me your new score, and I'll replace it. Awesome. We've been looking at momentum. We've been looking at collisions. So we have a thought puzzle. It says this: which would be more damaging, driving into a massive concrete wall, or driving at the same speed as the concrete wall into a head-on collision with an identical car traveling toward you at the same speed you're traveling? It's a trick question. Turns out both of these would be the same. Now, the key is that this car has the same mass as the red car and is traveling the same speed. Because what would happen in the brick situation is the car would give all of its momentum to the brick wall would absorb it, the car's final velocity would be zero, so the car's impulse would be negative mass times v initial, and then if you timed the collision, you could calculate the force. Here, because these are both traveling towards each other, the car has positive mv, the blue car has negative mv. Their momenta would cancel out exactly when they collided, and we would end up with the same situation as here, where our final momentum was zero, and our initial momentum was mv, and so it's the same impulse, change in momentum, and therefore the same force, assuming the time of collision is the same. Now, if the blue car was going slower, then the red car would actually have some extra momentum, and that would allow it to slow down and extend the time, and so that would do less damage. If the blue car was going faster, then the red car would actually end up getting pushed backwards, which would be an even bigger change in momentum and do more damage. And on that note, this is the final lesson of the unit. Next week, I'm going to be giving you a take-home quiz. And then the week after that, I'm going to be giving you some kind of an open book, work at your own pace test thing. By the way, there's talk that we may be back in June 1st. We have no idea what that's going to look like. Hopefully, you'll get a letter from the school district with more instructions. Probably it's going to be just coming in and working on homework. It probably won't be regular classes where your teacher is at the front of the room teaching. Okay? And as always, I miss all of you. Lesson 6, explosions. I don't know if you remember, but I said to you we use conservation of momentum when there's a collision or an explosion. I said I use it when there's a jeune. So, here is an explosion. A rifle bullet leaves the muzzle with a velocity of 6.0 times 10 to the 2 meters per second. If the 3-kilogram rifle is held very closely, what velocity will it recoil? So you might recall a while ago I showed you a video of a bunch of people firing an elephant gun, a big gun, where when they pulled the trigger, the bullet may have gone forward, but the gun shot backwards. And that's because momentum is conserved. It's a consequence of Newton's third law, forces come in pairs. But Newton's third law, forces come in pairs, is a consequence of the law of conservation of momentum. So I'm going to use, how about B for bullet, and I'm going to use R for rifle. You could use A and B, but the problem is since bullet begins with B, I'll use the B for the bullet. And we have an explosion. We have two objects. This is a job for conservation of momentum. So I'm going to say the sum of all the momentum that we start with has to equal the sum of all the momentum that we finish with. Before the explosion, before we pull the trigger, what's moving? The bullet, the rifle, both, or neither? And the answer is neither, which means, weirdly, our initial momentum is zero. Which also means our final momentum is zero, but I'm going to break that down because after we pull the trigger, I think both are moving. We're going to have the mass of the bullet, velocity of the bullet, and the mass of the rifle, velocity of the rifle. They're both going to be moving. The bullet's going to be moving forwards. The rifle's going to be moving backwards. They want us to find the recoil velocity of the rifle. So I think first I would subtract the mass of the bullet v bullet over to this side. And since there's a 0 over on the left, that's just going to give me negative mass bullet v bullet equals mass rifle v rifle. And now, what's the MR doing to the v rifle? Multiplying. So I'll divide, and I'll get this. The velocity of the rifle is negative mass of the bullet, velocity of the bullet, divided by mass of the rifle. Now, what's the negative telling me? It's telling me the rifle will travel in the opposite direction of the bullet. So if the bullet fires north, the rifle will recoil south. If the bullet is fired west, the rifle will recoil east. I'm just going to say forwards and backwards because I'm pretty sure we would always say that a bullet travels forwards. So the mass of the bullet is 0.06, that is in kilograms, so I'm good. Oh, don't forget the negative. The velocity is 6 times 10 to the 2, or 600. Mass of the rifle is that. I'm definitely going to get a negative answer. Is it 12? Should be able to do this in my head, but it's easier in my classroom when I have my game on. Yes, negative 12 meters per second. That means if this rifle, say, was just hanging from a rope, it would go shooting backwards at 12 meters per second. Now, in real life, the person firing the rifle cinches it against their shoulder. The momentum is transferred to their shoulder. Their shoulder rocks back, but they try and give a little bit and absorb that momentum. So these are what we mean by explosions. Usually an explosion has an initial momentum of 0 and therefore a final momentum of 0. Not always. An object can be moving and explode while it's on the move as well. Example 2. Spencer is sitting in a canoe floating on the water next to a dock. He decides to stand up and get out of the canoe. So he's going to stand up. Let's say the canoe is floating. The dock is to his left. So he's going to stand up and take a big step to his left onto the dock. Why will Spencer get wet? You may have seen this happen, or you may have experienced something similar if you've ever tried to balance on an inner tube while it's in the water, or if you've ever tried to walk on a stand-up paddleboarder. The reason Spencer is going to get wet is when he stands up, the momentum of the canoe and Spencer are 0, which means the final momentum of the canoe and Spencer have to be 0. So if Spencer gives himself a momentum to the left, the canoe has to get a momentum to the right, and it's going to shoot out from under his feet if he's not careful. Now, of course, in real life, what you do is you introduce an outside force to the equation. You grab the dock with one hand, and you keep pulling the canoe against the dock. Usually there's 2 of you, and one person pulls the canoe against the dock while the first person gets out, and then once that person is sitting out on the dock, then they hold the canoe, and the second person gets out. But if Spencer doesn't do that, he's going to get wet. So let's say it this way. If Spencer has momentum to the left, canoe must have momentum to the right, since their initial momentum is 0. You know what? Why don't I add that as a precursor sentence? Initial momentum of canoe and Spencer is 0, period. If Spencer, and by the way, so if Spencer steps to the left, the canoe is going to move to the right. And because Spencer probably has more mass than the canoe, for the momentum to be equal, the canoe is going to have to move to the right with a greater velocity than Spencer is stepping to the left. I used to teach canoeing at a summer camp, and I saw this happen all the time. And I would just laugh. Then I would teach the kids the proper way to get out. Okay. A 45 kilogram boy and a 60 kilogram girl are standing in the middle of a frozen pond. The boy gives the girl the push as shown. I'm going to use, how about G for girl and B for boy? So I'm going to call this mass G. That's a terrible G. And mass B. The girl moves backwards. I'll call this negative. With a speed of 2.4 meters per second, what velocity does the boy move off with? So there's two objects here, so we can say this is an explosion. The total momentum beforehand has to equal the total momentum afterwards. In fact, the momentum beforehand is 0. Because before the push, the boy was not moving and the girl was not. Nothing was moving. Which technically means that afterwards the final momentum is 0, but that's going to be because one's going to be a positive momentum, one's going to be a negative momentum. So I'm going to have mass of the girl, velocity of the girl, plus mass of the boy, velocity of the boy. They want me to find the velocity of the boy. I think I'm going to move the momentum of the girl over by subtracting it. I'll get negative mass girl velocity girl equals mass boy velocity boy, and then I think I'll divide by the mass of the boy. I'll get this. The velocity, change colors, Mr. Dueck. The velocity of the boy is going to be equal to negative mass girl velocity girl divided by mass boy. Negative 60 negative 2.4. You'll notice I'll get a negative times a negative, which is good because I already told you this velocity is positive. I said the boy, I'll call that positive. So this is confirming that I've got this set up correctly. Yay! Divided by 45. Also, I can predict, since the boy was lighter, but has the same momentum as the girl, the boy is going to be going faster than the girl. The negatives are going to cancel. I'm not going to bother typing them on my calculator. And I get 3.2 meters per second. B says, what's the impulse? Well, impulse is change in momentum, and I think I'm going to go mv final minus mv initial, because mv initial was just 0. So the impulse of the boy, and I'm just looking at the boy now, is going to be mass of the boy, v final of the boy, which is going to be 45 times 3.2. 144 kilogram meters per second. What's the impulse of the girl? I could calculate it, but I can tell you what it is right now. The impulse of the girl is going to be negative 144 kilogram meters per second, because the momentum was conserved. So if the boy gained 144 kilogram meters per second, then the girl lost negative 144 kilogram meters per second, if we call going backwards negative. If the push lasted for 0.25 seconds, what average force did the boy push the girl? Or did the girl push the boy, since forces come in pairs? Okay, well, I just figured out the impulse, so I think I'm going to use the fact that impulse also equals force times time. Force is going to be the impulse divided by the time. The impulse was 144 divided by 0.25. Dividing by 0.25 is the same as multiplying by 4, so it's going to be 576, I think. Double check me. Hey, I still got it. 576 newtons. By the way, the reason I said average force is it's possible the force wasn't constant. Maybe, in fact, probably wasn't. If you push off against somebody when your arms are really coiled, you have pretty good push. In the middle, not as good. And near the end, you have even stronger push, I think. So I doubt it's constant. Ooh, let's go to space. A space capsule consists of a 2,500 kilogram main capsule and a 1,500 kilogram probe. The space capsule is traveling at 120 meters per second when an explosion occurs. After the explosion, the probe moves forward at 280. What's the new speed of the main capsule after the explosion? Did they say explosion? Did they say jeune? This is a job for conservation of momentum. I'm going to realize that the sum of all the momentum that we start with has to equal the sum of all the momentum that we finish with. I wrote it there because I think I'm going to need lots of room. So I'm going to call this, how about C for capsule and P for probe? Works for me. Before the collision, what's moving? The capsule, sorry, the explosion. What's moving? The capsule, the probe, both, or neither? I think both, and I think stuck together. So I'm going to say this. Mass of the capsule, mass of the probe, V initial. Boom, there's an explosion. And afterwards, they're both moving, but separate. So I'm going to have mass of the capsule, V of the capsule, plus mass of the probe, V of the probe. You could call these finals as well, but I don't. We're okay. I think I can keep track of everything. They want me to find this. How would I get that by itself? I think first I'll minus this whole term over. The left side will just drop down like a domino. Minus mass probe V probe. And then I think it's going to be divide by mass capsule. That's the velocity of the capsule. Now, if I get a negative answer, I'll know that this explosion was so powerful that it blew this capsule backwards and gave this probe a whole bunch of forward momentum. That's possible. If I get a positive answer, I'll know that it's moving to the right. Now, I noticed that the probe sped up, gained momentum, so I can tell you this capsule had to have lost momentum, which means it's slowed down. I just don't know if it's slowed down so much that it's traveling backwards. So let's crunch the numbers. Mass of both, they actually told me it was 4,000. It says so in the question. And 120 minus 1,500 times 280 divided by 2,500. Brackets around the top. By the way, I hope you've clued in by now. If I'm going too fast, because this is weird not having people in the classroom with me, my timing's off, feel free to pause the YouTube video at any time to catch up while you're writing, if you're writing these out, or if you're just typing on your calculator with me or whatever. And I get, 24, let me double check, did I make a mistake? I don't think so. 24 meters per second. This is slowed down almost to 0 from 100. Not quite, it's still moving forwards, but barely. So, V capsule equals 24 meters per second. If they wanted a direction, they said speed, which is technically a scalar. If they asked for a direction forwards, or I might draw a little compass rose right here and call it east or something. B, what's the magnitude of the impulse given to the probe? Okay, the probe, well, impulse, which is change in momentum. I think I'm going to find that one by going mv final minus mv initial, but it's going to be m of the probe. So it's going to be mass of the probe, 1,500, times v final of the probe, which I think was 280, minus mass of just the probe, times its initial velocity, which was 120. 1,500 times 280 minus 1,500 times 120. The probe gained 240,000 kilogram meters per second. Where'd that come from? Well, the capsule, so this is the impulse of the probe, this is the impulse of the capsule, it's going to be negative 240,000 kilogram meters per second. Momentum's got to come from somewhere, so the capsule lost momentum, the probe gained momentum, if we call to the right positive and make that a gain. Now this said magnitude, so I could have left the negative off because the magnitudes will be the same. So explosions. Mountain climbers use nylon safety ropes due to their tendency to stretch considerably under stress. Using principles of physics, explain why. Well, stretching would increase time. Stretch means delta T increases. And since the impulse is force times time, now the impulse this person would experience while falling, I can tell you their final momentum would be 0. Their initial momentum would be their final velocity right at the bottom of the fall when the rope starts to jerk them to a stop. But as time increases, the force then would decrease. If we can lengthen out time, smaller force on the climber. And their mass isn't going to change, so it means smaller acceleration on the climber. And I think you might recall I said to you quite a while ago, it's acceleration that does the damage. Why does conservation of momentum explain why it's so difficult for firefighters to hold hoses that are ejecting large amounts of water at high speed? Well, okay, this is a good question. If before you turn the hose on, what's the momentum of the firefighter and the water? 0. After you turn the hose on, what must the momentum still be? 0. So if the water is moving forwards with the mass times velocity, that must mean the firefighters are feeling a force backwards with an equivalent mass times velocity of the water. Okay? Forward momentum of the water means firefighters experience backward momentum as a constant force. So what they'll typically do is they'll lean into it. They're not going to move backwards. Basically, the entire time, they're having to exert a force times time, an impulse forwards to cancel out the push from the hose backwards. I don't know if any of you are in the fire training academy, but if you've ever used a fire hose full out, it's got some kick. If you're doing it solo, you have to be fairly strong, and it gets very tiring very fast if you have that hose full bore going full out. Typically, firemen will work, I think they'll typically use a hose in a pair if they can. Example 7. The diagram below shows 2 pop cans of unequal mass. In fact, it looks like the right-hand can is exactly twice the mass of the left-hand can. Suppose we detonate an explosive charge between them, and they fly apart. What can be said about their velocities after the explosion? They'll each have the same momentum, but what? I think smaller can will be going twice as fast as the heavier can. Instead of smaller can, I should have said lighter can, because smaller implies size, lighter implies mass. It says, using principles of physics, explain your answer. Ooh, let's do a lovely algebraic proof, shall we? Before the explosion, we have 0 momentum. After the explosion, we have mass of can 1, velocity of can 1, plus mass of can 2, velocity of can 2. I'll call this mass 1, I'll call this mass 2. Let's get velocity of can 1 by itself. So we're going to subtract that over to that side. We'll have negative mass 2, velocity 2, divided by mass 1. That equals the velocity of can 1. Now, negative mass 2 is actually 2m. Velocity 2, I'll call velocity 2. Mass 1 is actually m. And we end up with the velocity of can 1 is negative in the opposite direction, but twice as big as the velocity of can 2. You could also have made up numbers and just crunch the numbers, but I did this one algebraically. Ooh, we've come a long way. So that kind of brings us to the end of the unit. I do have a review assignment. I'll probably send that out along with the take-home quiz next week. Okay? Number 1. Number 2, this is meant to be stuck together. So this is a collision. This was at rest. This was traveling at 5.2 meters per second. Afterwards, they stuck together. Find the final velocity. Same idea here, except here they're both moving. Before the collision, they stick together after the collision. Similar here, similar here. Oh, here they don't stick together because there's a gap between them. And here, notice they're going in opposite directions. Let one way be positive, one way be negative. I just wanted to give you a bunch of different collision scenarios. It's kind of pretty much every possibility I could think of. Number 3, this is really, really similar to the boy and girl that pushed each other on the ice. Number 4, this is also really similar to the boy and girl that push each other on the ice. 5 is good, 6 is good. I'll skip the spider question. Eight is good. Nah, 9 I'm going to skip. Ten is kind of a nice thought puzzle. Skip to 11. Twelve is a challenge. See if you can handle 12. I'll skip 13. All right. Hope you're all doing well. And again, I miss you infinity. I really do.